Um, to start off, flow simulation, we have three very good and very important enhancements this year. The first one is mirror results for symmetrical models. The second one, mesh settings, which is where I'm probably going to spend the majority of our time for flow simulation enhancements today, just because during the rollouts I kind of presented it. There's a new mesh settings, but I didn't really dive too much into it because we didn't really get that information just yet. But now we have more information on how the new mesh is set up, so I'll share that with you today. And then we will close the flow simulation enhancement with the transient and analysis improvements. So first off, mirror results. Now in Solidworks 2016 for flow simulation, when you run a symmetry analysis, so if you have a computational domain which is only the half of your model, you will only get half the results. And that's kind of how it looked previously in older versions prior 2015 and before. So this is a cut plot and this is a surface plot. But now in 2016 you have an option right when you create that cut plot or surface plot to check mirror results, and essentially this will propagate those results over to give you that mirrored view. So I think this works well for cut plots such as this, and even better when you have surface plots. I think this view is just kind of speaks very loudly because you can actually see the section view of that pipe, kind of moving in and out, and you can also see the surface plot clearly. And depending on what you're trying to show, whether it's pressure or velocity or temperature, you'll be able to see that contour very easily. Okay, so the next thing what we have is the new mesh setup in 2016. So the global mesh and the local mesh interfaces for specifying your mesh has now changed. It is, in my opinion, it is definitely more flexible and easy to use, and it's become very similar to SolidWorks simulation, where you will actually access the mesh right within your analysis property manager or analysis design tree right here. So the mesh, the level of initial mesh setting will no longer exist in the project wizard. So if you recall in previous version, when you start the project wizard, you will go through the process of setting up your initial conditions, your boundary conditions, and then the last page it will give you the initial mesh setting page, which will allow you to drag a slider between 1 to 8 and set up your mesh in that wizard. Well, that's no longer the case. The mesh setting is now within the design tree here, the analysis tree. And essentially, you will right-click mesh and select on global mesh. So initial mesh now is called global mesh. So one of the biggest changes in terms of the mesh refinement level is that it no longer has 8 levels. So in 2015 and before, you had level 1 all the way up to level 8. In 2016, there's only up to level 7. So whatever analysis that you have set up prior to 2016 at say level 8 will automatically turn to level 7. It will have the same same mesh level, refinement level. It's just a drop in the number of how it increases from mesh level to from one to another. In 2015, the base mesh, level 5, 6, and 7 had the same base mesh. So the base mesh itself did not refine. I know in level 6, 7, and 8, they had a automatic mesh refinement, which we're going to talk about a little bit more towards the end of this this enhancement. But now you, when you set up your mesh levels, as you increase this, the base mesh is refined at every level. So now that's an automated process that's going to create a much better mesh for you, and that is one of the major reasons why they were able to remove one of that gradient level, or the level to, to increase to a better meshing. Minimum wall thickness setting. So this has now been actually hidden by default. So if you, again, if you recall back, even for some of you who are using SolidWorks 2015 or prior, right now, you'd be able to see that option right in the that meshing splash page. So now it's actually hidden by default. And the reason for that is because moving from 2016 onwards, there's actually much better ways to refine your model, especially when it comes to a wall thickness. It has actually become less important to refine a wall thickness, and we're going to talk about some other refinement tools that have been added on as well. There is quite a bit of information here as to why this tool has been hidden. It doesn't really require much user control anymore. But of course, if you need to, if you find the need to control that, you can always bring it back up manually. So if you actually go into your SolidWorks tools, flow simulation tools, under options, in the options dialog, there will be a display wall thickness. You can just change that to always, and that will show up in that in the mesh control. So if you just go if I go one page back, you will see that mesh wall thickness setting is actually not present right here. But then once I change that option, it actually shows up in here. So just so you know that this actually is automated as well right now. It takes into consideration the geometry that you have, as well as the narrow channel that the wall has been created for, and it will refine that number for you. Again, so it doesn't really require much input from the user. And it's not as important as an actual narrow channel setting, because in a narrow channel there's actual fluid flowing through it, and you want to be able to refine that, because typically that's where you're trying to get your results from. But in the wall thickness, it actually shares a mesh. It shares a solid mesh and fluid cell mesh. So it's actually less important, and a lot of it can be automated right within SolidWorks. So basically one less thing for you to worry about now in terms of meshing. The next thing is close thin slots. So this is a new option that's been added to your global mesh setting. So this allows you to specify the size of the model's flow passage that you want to fill with solid. Now, I really sat and thought about this for a second. Why would someone want to do this? Well, then it hit me. I think the best use for this is when you want to test, quickly test for different slot sizes, right? So if you have created a geometry of a certain slot size, now if you want to reduce that slot size, you can actually put in that number, and it will fill it with a solid. And then you can basically rerun your analysis and get your new results to see what type of flow you have now, as that slot has started to grow smaller due to this feature filling it up with solid material. So this is a new feature again right within the global mesh setting. If you check that, you will see that that option that shows up right there. The next thing that I wanted to talk is display refinement level. So this is a very nice tool because it allows you to check your refinement, your global mesh refinement early on, so you don't actually have to run your mesh. So typically in previous versions, if you want to check your mesh, you would actually have to mesh the analysis. Well, you don't have to solve it, you can just mesh it, and then you can actually view the mesh and then make changes, remesh it, make changes, remesh it. Well, that's really not the case anymore. If you check this display refinement level right within, again, global mesh setting, you can check this for your X, Y, and Z planes, and also for components. So if you select that component option, you can select the component, and it will show you the mesh refinement at that component. So just keep in mind, this is not taking into account your current mesh settings. It is just kind of giving you an idea of how dense or how coarse the mesh is going to look depending on that mesh refinement level. So you can see that there's 0 to 9 here. So as I slide this up, it will show me kind of how that mesh is going to look. Now, the best part about this is right within the graphic window, you'll be able to just basically hover over any of the cells, and it will tell you the size of that cell. So in this case, it's probably all going to be the consistent thickness, all going to be the same, because I'm not really using manual techniques here, just automated techniques. So as I hover over it, it will show me the size. So if you want to take a look at this, maybe we can hop into SolidWorks real quick, and bring up this option. And if you look at the mesh, I'll go into my mesh option right here, edit definition, display refinement level. You can see that I have my front, top, and right planes are all selected. If you deselect, it just goes away. And I can increase the refinement level. You can see that it's in real time. It increases it in real time. And if I want to see the size now, I can just simply select on this show cell size right here in the corner, the bottom right corner, select on that, and as I hover over my mesh, you can see that it's telling me what the size is. So in this case, it's all the same. Again, I'm just using automated mesh right now. I haven't really done any initial mesh or local meshing to create different sizes. Okay, very nice tool, and then I think it's really going to help in terms of meshing when it comes to SolidWorks flow simulation. Okay, so let's go back to my slides here. All right, so now that we've talked about the global mesh, let's talk a little bit about local mesh settings. So, so local regions can be defined by a component face, at edge, vertex, or by simply by simple geometric shapes. So this is not changing. This has always been the same. So if you select some component or some edge or vertex, it will refine the mesh that touches those components or touches those entities. You can also refine mesh using a dummy cylindrical model, cube, or sphere that sits in place, and you would be able to mesh that. So say for example, if I have a model like this, I can actually create a cylinder piece that just goes right through this piece right here, and I can create a mesh refinement just for that. So what that will do is it will actually refine the fluid cells that is, that because of the fluid flowing through this piece, it will refine the fluid mesh, and just within my calculation control options, I can say to disregard that dummy model. Don't take that into account when you're calculating your results. So that's always been there. And of course, as you know, the local mesh setting has a higher priority than the global setting. So it doesn't matter what you set in your global setting. If you set a local mesh setting, it will override your global setting. However, a new addition to the local mesh setting is the Equidistant Refinement. This is a great tool. I've been testing this out quite a bit, and it's worked well. It's very easy to set up, so before I jump into that again, if you want to access your the local mesh, you just have to right-click the mesh in your design study tree and select on Insert Local Mesh, and then you'll be able to access this, create this page. So let's talk about this Equidistant Mesh Refinement. It basically comes down to two settings. It's your defined shell offset and your how many cell layers that you're going to basically create for that mesh in your model. So in this case, you can see that for your mesh level right here, or your shell offset, you can only create up to 3. So you get to create, so you can see here I have 1, 2, and 3. So the first one is 0.05 from the source, so a face that I'm selecting. And then the second would be 0.01, so 10 meters. Again, this is from the source. And then the second is 20 millimeters from the selected source. So you can select 3, and then you can select how you would like to refine those different levels. So let's go ahead and take a look. So I have some PowerPoints here that show the combination of these. So before I jump into this and show the combination, let's actually go into SolidWorks and kind of see this in action. So let's see. Yeah, this is the model. Let me go ahead and load my results here. That's loading. Alright, there we go. So you can see that for this, I actually don't have to solve for the entire analysis. I can just mesh it, right? So when you hit for your run, all you need to do is just check mesh and then hit run, and you'll already be able to get some mesh plots to at least check your mesh, see whether you have a healthy mesh. It's a good time-saving technique. So right here, if I say show, you can see that this is a mesh refinement using Equidistant mesh, and my setting here, you can probably already guess just by looking at the different layers. I have 5 maximum equidistant levels at 3 layers. So the first one was 5 millimeters, and then the second one was 10 millimeters, and the third one was 20 millimeters. After that point on, it really doesn't matter. I mean, because you already have 3 layers at that point. Let's take a look at my PowerPoint to see the combination of the different combinations of this. So this is one Equidistant shell, 10 millimeters from the source, and 1 layer. This is 2 layers, 3 layers, 4 layers, and we are still just talking about one Equidistant shell. So the second, third, fourth, and fifth layers doesn't really have any type of distance control right now. It's really just one element, and they take that element. So if you have 1, you can see it breaks into 4. That 4 breaks into probably 16, and then that 16 breaks into smaller, and so on and so forth. So 2 equidistant, so now I have 5 millimeters and 10 millimeters, so 5, and 10. And you can see so on and so forth here. So this will be, I think, a really good technique to find convergence. So once you've set up your meshing, you can add layers and add some different equidistant shells and see how your results are converging. So great way to set up some refinement. So this is a big news for us. Solution adaptive mesh refinement. I kind of mentioned earlier in the beginning of this, where in previous versions, whenever you pull that mesh style up to 6 and above, there is a solution adaptive mesh refinement going on in the background. It's automatic, and essentially what it does is it will refine your mesh as it's solving your analysis. So if it requires some better refinement in certain areas, say especially where you have fluid cells, it will refine it automatically for you. This is no longer the case in 2016. They have removed that adaptive meshing. And again, the reason for this is because there's a lot of techniques now that's going to make it much easier for you to set up refinement early on in your process. So you don't really have to just allow the software to do it automatically and not truly understand what it's refining or how it's refining. You'll have kind of full control of doing that. Now, it's not automatic anymore. However, it still can be set manually. And this is also an added advantage, because in previous versions, it was automatic from 6 and above. But now, in this version, you can set that refinement at any level that you want. So level 1 to level 7. And you can set up those refinement properties, and you can allow the software to automatically refine as it's solving and getting results. All right. Okay, so that's really all I wanted to talk about the new mesh the new mesh interface for flow simulation. I could easily probably spend a whole other hour just talking about all the different settings and the best settings for it. So which is something that I'll probably will do in the near future as we find out more and more information about using this new mesh setup with flow simulation. So look out for that. I'll probably have a webinar sometime perhaps in a few weeks or a few months that talks a little bit more about the healthy mesh settings for flow simulation. Oh, and just one more thing, just to kind of reiterate again, if you have already set your mesh before in previous versions, not to worry, all that will translate over into the new mesh setup within Solidworks 2016. So there's not going to be, you're not going to lose any results or your mesh settings, none of that. Okay, so next thing I want to talk about is the new nested iteration time-dependent solver. So this can be found right within your calculation control options. So calculation control options is actually right within your input data. Perhaps if you're not sure where it was, right click your input data, calculation control options right there. And now you'd be able to select nested iterations, and what this allows you to do is very similar to steady state solver, where you can actually set up the number of steps to the number of iterations, nested iterations, to solve your analysis. And this is a huge time saver. It is recommended for all transient problems with supported physics, particularly in electronics cooling applications. And really, from what we've seen in the past, only class problems which you really need to understand viscosity effects between iterations, such as the first and second Stokes problem. That's when I would say you can revert back to the default transient solver, where it kind of solves for every step. In this case, the results is still pretty accurate, so what better way than to look at an example that you guys can try out as well. So the example that I've chosen here is the plate fin heatsink cooling by forced convection. This can be found in the validations PDF document, and default location for that is your SolidWorks installation location. So C program file, SolidWorks flow simulation, language English, docs, and you will find a validation.pdf, page 65 to 68. You have this example. So I'm not really going to go through this example, but what I really wanted to show you is, or what I wanted to talk about is the solver, kind of what went into solving it, and how the results, how close or how accurate the results was using nested iteration. So what we did find was that the CPU time to solve faster for the default time-dependent solver at each, the CPU time, so the CPU time was a lot faster for the default time-dependent solver. So then you might ask the question, well, if the default solver is faster, then why would I use the nested iteration, right? The nested iteration option allows you to use a higher manual time step with better accuracy and reduces the overall CPU time to solve. So it actually will save you much time because it increases your accuracy. So if you look here, with the old default transient solver, CPU time to solve, this was in seconds. So when we set it to automatic, it really dropped it down. It created it to 0.0026 seconds. So it really took into account every iteration. And our results that we got was 325.75 max temp. And this is for a surface goal for Kelvin. So what we would deem the most accurate results running a default analysis. Now when we change that default analysis and we drop that down to 0.3, the time to solve, 0.3 seconds, the time to solve decreased significantly, but then now your accuracy is dropping quite a bit. So this dropped to 3.25.49. When we increase the time step to 3, time to solve again much faster, but now you've already lost 2 Kelvin there. So this is quite significant for a temperature. You want to get very good temperature results. And temperature is one of the easiest calculations to do in computational fluid dynamics. You can see that when we went to manual 300 steps, we were down to 3 seconds. So it really solved almost instantaneous. But at this point, we already lost 4 degrees temperature in our results. Now, on the other hand, if you take a look at our nested iteration, when we used 0.3, our time to solve was still probably about 10 times more than the default, but we were still pretty accurate, pretty close to our auto step. And as we drop it down further and further down, we were, let's say at manual 30, we were still in the range of 325 with 325 Kelvin, which is within the same degree, and the amount of CPU time to solve. Now this is the comparison that we should make, right? 164 seconds comparison to 1200 seconds here, right? So again, that's kind of the I guess the catch there is it's not going to completely remove or decrease your computational time, but it's going to decrease it without sacrificing your results or the accuracy of your results. So I think a better representation of this, if we put this on a plot, and you can see that for our nested iteration manual time step at 30 seconds for 600 total physical time, we were pretty close to the default auto time step, right? You can see that that orange right there, the yellow and the orange was pretty much pretty close to that green value right there. You can see as we are leading up to it, the results might not be so good. So as I mentioned earlier, if you want to know what's going on between iterations, maybe the viscosity effect between each iteration, your results is not going to be very good, but your final end results, you're going to get pretty good results. All right. So now if you're just comparing apples to apples, where we want to get the same accuracy results, same accurate results, you're going to be saving about 80% time, so 80% faster. All right, so there are some limitations to this. It's a fairly new tool, so no rotation mesh. So sliding mesh, or the rotating mesh that they introduced last year, where the mesh changes as your part rotates, and that's not it's not supported right now. So if you have any sliding mesh in there, you can't use this nested iteration solver. No condensation, humidity, steam, or real gas. No cavitation problems, and no high Mach numbers as well. All right, so that's really all I wanted to cover for flow simulation. I have about it's 12:35 now. I have about 15 minutes more, so let's kind of spend maybe about 10 minutes with simulation, and I'll just leave the last 5 minutes for questions. All right, so the four enhancements I want to show today is the releasing prescribed displacement. I think this is a great tool, great new enhancement. Alternate curvature based mesh, so they introduced a new mesh. Sectioning the mesh, this has been a long time coming. We've really wanted this for a long time. And detecting unconstrained bodies. So first off, now you can release prescribed displacement. So as opposed to pushing your part down to 0, you can think of it where you're pushing on a plastic piece, and rather than pushing it back to 0, you can just let go, and it will slowly come back to its original location. So there's actually an artificial damper going on in the background here, so it's not really it's not really kind of going back to just bringing back to 0. There's some mathematical automated damping that's going on there that's slowly pushing that plastic back, but it will allow you to basically off your displacement. Okay, so this can be set up right within the your prescribed displacement using a chart. So now you would have a drop-down menu where you can just say 0 to 0, 1, and then you can. So this is your time. So at 0.51 seconds, you will just release it, and it will just allow it to come back to its original location. All right, so the next thing that I want to talk about is your simulation measure. So right within your mesh parameters, as you recall, before you only had standard mesh and curvature based mesh. Now we have a blended curvature based mesh. So that's a new mesh option there, and it has actually reduced the number of nodes and elements significantly but still giving quite good mesh um, results. So if you look here, these are three mesh that we created for the same part. This is your standard mesh. You can see this is pretty coarse. Probably wouldn't give us very good results. And we already had 53 nodes and 53,000 nodes and 32,000 elements. When we move to the curvature-based mesh, which is what we've always suggested to use when you want to get the final best results, you always want to use curvature-based mesh. This bumped it up to 667,000 nodes and 435,000 elements. Now, with node and with such a high number of nodes and elements, you can probably tell that this would take quite a bit of time to solve. The meshing itself, this is the amount of time it takes to mesh, so 29 seconds. But when you're dealing with this higher number, you're going to have a significant amount of time that you'll be waiting in comparison to the standard mesh. However, now with the alternate curvature mesh, you can see here, blended curvature based mesh, we have a combination of standard mesh and curvature mesh, which kind of gives us a middle number now, 100,000 total nodes and total elements 66,000. And from what we've gathered, the results is very comparable to your curvature mesh. So we're getting pretty good results with lower number of mesh. Again, better refinement without sacrificing your accuracy. That's, I think, a win-win. So very good addition for SolidWorks simulation. So this is something that we all have been very excited about, mesh sectioning. Before, we were kind of in a black box when we were meshing in terms of thickness throughout the part. We couldn't really see the ratio or the mesh quality through the thickness of the part. It may seem like it's doing well, especially in curvature, in curved areas from the outside. From the inside, perhaps not so much. So by creating a mesh sectioning, you'll be able to now clearly see how it's meshing across your thickness. Now this is fairly important when you're dealing with parts with varying thicknesses, and you're using some global mesh setting there, and you're not using any type of initial mesh initially. You could create your global mesh and create a mesh sectioning, and then select certain edges or faces to create your initial mesh. So this will also help you to create a better mesh as you're creating or refining your meshing. To access this mesh sectioning, you would have to go under your mesh quality folder. You would create a mesh quality plot for that mesh, and then you would right click that mesh quality plot and select on mesh sectioning, and that will give you the option to select a plane, actually probably not even a plane. Let's actually take a look at that. So we're gonna turn on SolidWorks simulation here. Show that. So let's go ahead and mesh that real quick. So you can see here I'm actually going to use that blended curvature based mesh. give it a few seconds here. So as this is meshing, talk a little bit more about the mesh sectioning. So again, when you basically, all you have to do is just right click the mesh quality, select on mesh sectioning. So it's very similar to your section tool. You will be able to see it in real time. You will be able to, there will be an arrow there, and you would you'll be able to see that changing in real time. So I'm going to show this, and right click mesh sectioning, and you can see I can select the plane that I want to reference, and that's the arrow, and as I drag the arrow back and forth, you can see how that mesh actually changes as it's going through the thickness. Say okay, and then now I can actually scroll in and take a look at my mesh. Okay, so it's a great tool, and I think it's going to give you much healthier meshing, which in turn will give you much better results. So the next enhancement that I wanted to talk about is detecting unconstrained bodies. So this is a really good enhancement, a very useful enhancement, especially when you're dealing with large assemblies, and you would have to, you can't always just say bonded connection and run your analysis, right? You want to have some no penetration connections in there, or you want to have some allow penetration in there, really depending on the type of assembly you have, and and you want to create some type of fixtures. You're not going to always say just fix the entire part. You might want to give it some rotation. You might want to give it some translation. You want to allow it to translate in a certain direction. And when you're dealing with a high number of parts in your assembly, that can start getting tedious, because there's really no way of keeping track of that besides manually doing it. You have to kind of keep it in your memory what you've done, and or kind of just do it in one go. And that becomes a bigger problem when you have somebody else who's setting up that constraint for you, and then you take over the model, and now you're stuck with the under constraint model, and you're not really sure what's in there already. Well, if you right click connections now, it gives you this option to select find unconstrained bodies. So in previous versions, you know, in our simulation tips and tricks, we always talk about this. If you want to find unconstrained bodies, run a frequency analysis, and it will basically, parts which are not constrained will fly out or fly away in your frequency analysis. This will now allow you to do this in a much better fashion, as opposed to running a frequency analysis and not really understanding what's going on. So all you need to do is hit calculate, and it will show you the bodies that are not constrained, and it will also show you how it's not constrained. So every body has 6 degrees of freedom, right? We all know this. There's 3 translations and 3 rotations. It will show you it's not constrained in a certain translation, 1, 2, or 3, X, Y, or Z, or rotation. So actually, let's take a look at this right within SolidWorks, so we can actually view this. So let's see here. Green. Right-click connections, find under constrained bodies, and I'll say calculate. So what this actually is doing, it actually is creating a frequency analysis for me in the background, but instead of just giving, having me guess what's going on and how it's not constrained, it's giving me a nice window here that shows exactly the bodies that are not constrained and in which direction. So when I select on a body, it will highlight that body, and as I select on the translation, it will show me the direction in which it moves. So this one is in the X direction. You can see here it's moving like that. This is going to be in the Y direction, moving up and down, unconstrained, and this is in the Z direction, right? So it's unconstrained. And of course you also have rotation. So in this example here, what we have is pretty painful. When we look down this list, we have 32 unconstrained bodies, and typically when we have something like this, and if you come to tech support, and if you call us up and you ask, hey, what's going on, we typically know that this is usually because there is some gaps in your model, and we all know that we have solid gaps. We can use some incompatible meshing to deal with that, and basically say to disregard the gaps between solid bodies. But we've not really been able to do that with surface bodies till 2016. So now with 2016, if you right-click your component contacts, where you can go into your global contacts, there's actually an option here which is non-touching faces. This already has existed, right? So if you hover over here, it says, well, not in here, but if you go into your help, it will tell you that the reason for this is if you have non-touching faces, if it's below this number, it will disregard that number and bond it. Well, this was only available for solids, but now it's available for shell edge and solid face and shell face as well. Okay, so in this example, this has shells in it, and it will work flawlessly. You wouldn't have any problems. You just set that minimum clearance, and we should be all set there. All right, so back to my PowerPoint. So that's really all I had for today. I'm at 12:50 right now, so I have a few minutes for questions. Any questions? You can actually type it in. There's a questions panel there, and I'll be more than happy to answer. Okay, so seems like no questions so far. Please feel free to give us a call, tech support. If you upgrade to 2016 and you start using some of these new tools, we'll be more than happy to hop on a web meeting with you and talk about it a little bit more. Thank you for joining me today. Again, as I'd mentioned, as we find out more about the flow simulation mesh setup, the new mesh setup, I will probably create a webinar like this in a couple of weeks or a couple of months. So, oh, one question: are there any changes with thermal analysis study? No, there has not been any direct changes with the thermal analysis study. It's the same. They have not added or removed any tools from thermal analysis. Okay, so I think that was the only question. All right, so again, thank you for joining me today, and for more videos like this, please go to our YouTube site, CAD Dimensions YouTube site, and you'll be able to view those. Thank you, and have a great day.
Don't forget to check us out on YouTube, Twitter, Facebook, and our blog for more great content by clicking on the links in the description below.